Hey guys, so today we're going to be talking about erosion and deposition. This is a continuation on our unit on weathering, erosion, and deposition. This is for our earth science students, so feel free to take any notes, pause whenever you need to, make sure that you have all the details that you're going to need for this. If I talk a little bit fast, I have no problem with you stopping, pausing, rewinding. But if you enjoy this video, please like and subscribe, share if you find it useful at all. Otherwise, let's get going and let's talk about what we need to talk about. All right, so we're going to talk about erosion. So what is erosion? Well, very simple. Erosion is basically when you transport weathered material from one place to another place. So what are we talking about with weathered material? Remember, we're talking about material that used to be a rock, used to be part of a mountain, used to be part of a hill, and has been broken down. So now we have these broken up sediments, which are the pieces that we have after we have performed this weathering. Now this weathering could be physical, like frost wedging. This weathering could be chemical, like oxidation, or any of the other ones that you've talked about in class. And we have all this pile of material just sitting there, and we need to move it from one point to another point. Okay, now erosion can happen naturally, or it can happen through man-made means. Obviously, for this purpose, for the purpose of this lesson, we're going to talk about the natural means. So we're going to talk about the natural things that will cause erosion to occur. So when we talk about naturally occurring erosion, we talk about what we refer to as the agents of erosion. So there's a couple of them. We have gravity, we have running water, we have glacial ice, we have wind, and we have waves. These are all natural things that will move material from one place to another. So rocks falling down a hill is gravity. Running water is a stream carrying pebbles or dissolved substances in it. Glacial ice, glaciers carving their way down through valleys. Wind blowing little particles of sand. Waves moving material from the deeper part of the ocean towards the beach. All of these things are what we're talking about. We'll focus on each one. We'll focus on erosion as a whole, and we'll give lots of images and lots of pictures so that hopefully you can understand what's going on. So the first type of erosion that we're going to talk about is gravity erosion. So gravity erosion is often referred to as mass wasting. Okay? So when we talk about this word mass wasting, what we're talking about is basically the downhill movement of rock or soil due to the influence of gravity. So gravity is what's pulling all this stuff down. It's anything that has mass, gravity will affect, so it's pulling it down the hill. And it's a natural geologic process, which means it's something that happens on Earth. Usually when you have weathering, you have a rock that gets broken up, gravity's going to pull it down. Now there are lots of different types and lots of different things that affect whether we have gravity erosion or not. So, if we're talking about mass wasting, once again, what are we saying? We're saying that gravity is the controlling force. It's going to be the thing that is directly causing all of these different aspects to happen. Okay? Now, there are different things that can cause mass wasting or gravity erosion to happen. First thing is you could saturate whatever material you're talking about, whatever sediments you're talking about, with water. You can fill it through a rainstorm, through a dam breaking, through just basically a filling of water. Now what's that going to do? That's going to fill in all the little pores and all the little gaps between the little bits of sediment that are there. It's going to minimize friction. It's going to lubricate surfaces. It's going to affect things like adhesion and cohesion and all these things that you've talked about. Obviously that's going to make it easier for gravity to pull things down. Over steepening of slopes. What does that mean? Basically, if you make the hill steeper and steeper and steeper, then your gravity is going to play a more important role. As the vertical component of gravity gets more and more and more closer to the actual just pure force of gravity, you're going to get a lot more gravity erosion occurring. That word sounds weird. Don't worry about it. You'll learn it when you get to physics later. But basically, if you make the hill steeper, you're going to get more and more of this gravity erosion occurring. If you take away vegetation that's there, when we clear trees, bushes, ground vegetation, all that stuff does a really good job of holding the dirt in place. Anybody who's ever pulled up weeds in a garden understands this basic concept. The roots of plants can help to hold the soil in place. It doesn't get washed away as easily when you have lots and lots of vegetation. If we remove that vegetation, that's going to be a big problem, and you're going to get a heck lot more of this mass wasting. And finally, obviously, if you have an earthquake, the vibrations that happen in the ground, the shaking of all those particles is going to make it a heck of a lot easier for the material to end up sliding down the side of a mountain or just moving in general. When we talk about different mass wasting events, so times when mass wasting is going to happen, there's going to be a couple of things that we use to kind of classify them. Okay? The first is going to be the type of material involved. Do you have debris? Do you have mud? Do you have just earth? Do you have rock? Debris would be a mixture of rock and silt and sand and all the things that are there. Mud is going to be soil that is heavily saturated. It's full of water. Earth, you're basically just talking about soil. And rock, obviously, pretty self-explanatory. So which one of these you have is going to determine the type of event that we have. We're going to classify them and name them in about a slide or two. Okay? The other way that we can classify mass wasting events is by how fast we move. So if we have material that's moving very, very quickly, we would say that's a fast mass wasting event, sudden, or we could have a slow, more steady sort of thing that's going on. So there's mass wasting that's always occurring. That would be your slow movement. And then there's mass wasting that happens very rapidly. This would be things like rock slides or mud flows or things like that, lahars and things like that. So when we look at them, we want to say, what is it that's involved, what's the debris, and how fast is it going? Those two things are going to help us put together the idea and name the mass wasting event in question. So if you look at the image here, you have lots of things that you can kind of point to and understand as a particular event. So right here, if you look on the screen, in this picture right here, you have slumping forming. That would be what happens right here. Okay, we have these sections probably of saturated material that are just coming off in large chunks and just kind of sloughing off down there. You don't have the whole surface doing it, but you can see that you get a little bit of soil creep going on here, where you can see that it's slowly like creeping along and working its way down. So that's where you would have sort of slumping and creep going on here. Here you have mass slumping, where you can see these large sections are breaking off. A lot of times you get stuff like this when you have tectonic activity. The Alaska quake of 1967, 47, the biggest quake in the Americas, was an example where you had mass amounts of this happening in parts of Alaska. This image right here, you have a lahar. Lahar is a volcanic mud flow. A lot of times if you have a volcano like the one up here and it has an ice pack on top of it, when the volcano goes off, all that ice is going to melt really, really quickly. It's going to mix with all the dirt and debris that's collected along the side of the volcano, and it's going to create these massive mud flows that we call a lahar, the word that you see right here. Okay? Or if you just get heavy rainstorms, you can get that as well. If you just get a massive amount of wet, damp soil just moving very quickly downhill. Here you have a debris flow. You can see down here you have a mixture of mud. You can see larger boulders and rocks that just came down here, most likely, once again, caused by heavy rains and things like that. And then in your last slide here, you can see you have a much more solid surface, and you have a rock fall or a rock avalanche here, which could be quite deadly, obviously, if you were down here on the road and you got caught in it. So you have a couple of examples for this. This might be a good idea to stop the video here, snap a screenshot, record this, make sure you label these things so that you can be able to reference them in the future. Okay, here's an example of slump at Point Fermin in California. And if we look here, here you have the rock right here. You had material here. There was a road, obviously, you could see that was running right through here. And these portions of the hill just slumped down towards the ocean. There was probably some undercutting that happened down here because of the oceans eating away at this. Eventually gravity won and it just pulled these levels down. You can see how it broke through a rock here, through a road here, and how dangerous that would be. In the video we're about to watch here, what you're going to see is a rock slide actually occurring. So here's an image of what you would see in a typical rock slide like this. You have a solid surface here, and there's some sort of a rupture. It could be because of an earthquake, it could be because of frost wedging, it could be a large amount of things combined into here, and what ends up happening is these chunks of rock just basically come down the slide, gravity wins, and they can cause damage and devastation and cover up roads. For example, here you see an image of a rock slide that's covering a mountain pass. Hopefully there was nobody underneath there, or they're going to have a nice insurance bill. If you want to see what one actually looks like, here's an actual one actually occurring in real time. So you can actually see it here. You get a little trickle that starts there, and then the whole rock surface just comes down. A lot of times if you're driving on highways or places like that, what you actually might see is rock walls will have a netting put around it to prevent this sort of thing from happening. In my neck of the woods in the Northeast over here in New York, if you ever drive on the New York Thruway or even parts of New York City, particularly areas right around like the George Washington Bridge and the Cross Bronx, if you look on the walls, you'll actually notice that there's netting against the walls there. That's to catch any rocks that might happen. They're inspected quite regularly to prevent this from happening and obviously hurting anybody. Okay? A debris flow or mudslide, very similar, except what you're talking about is massive amounts of wet soil just coasting down the side. So here in the image you can see you've got rainfall happening on a steep slope here. As that rainfall happens, the material in the hills is going to get more and more loose, and eventually gravity is going to win and it's just going to pull it right down the side. There might have been a house right underneath here, and what you're going to get is something that could be quite dangerous if you were trying to, live there. Okay, so here you have images of a mudslide. Okay, you have a river here that's choked with all sorts of debris. Right here you have the after effects of a lahar. So you can see how this could be quite dangerous to obviously populations and travel routines. If there's bridges going across these things, it could be quite dangerous. And here you have an active mudslide going into a river. Thankfully, you don't see a whole lot of devastation or anybody getting hurt, but you do see these people as they're going by in a boat. You can see it tearing down some trees there. So it does pack quite a wallop as it does move down the sides of hills. Now, another form of mass wasting that you can get is what we call earth flow. So earth flow happens when you have hills in areas that are very humid, very damp environment. So already the ground is kind of naturally saturated based on the climate and the environment that's going on. And when the water just fills up that soil, it's going to cause portions of it to easily be able to slump off, particularly if you have clay and or silt making up the majority of that particular soil. So that could be a problem, and what you'll basically get is these areas that just kind of slough off and come off. If you're in an area that's not necessarily humid all the time but has received large amounts of rain over an extended period of time, this process can also happen in those areas. And so you'll get that process going on in those particular areas. And that is what you see in this particular area. So here you have water in a small ditch because of a recent storm, and this soil right here on this hill has had that happen. And so what you can basically see, and they show you in the image, is you get this clay-rich soil on top here that has just kind of flowed down towards the water area and left this sharp cutout that we call a scarp as it has moved downwards through it. Okay, now those would be relatively fast in that you could see them happen in a moment. If you watched it, you would actually see the process. There's tons of videos on YouTube where you can watch all these crazy events happen. But one of the slower events that you can get is what we call creep. Creep is a gradual movement. So soil moves particle by particle by particle on its way down a hill. Typically this is going to happen because as you change temperatures, you're going to get this alternating expansion and contraction of the surface material, and what that's going to do is basically it's going to cause the soil to slowly move downhill. And so that's what you see in this image right here. Okay, here you have soil sitting on top of the bedrock. Okay, and what's going to happen as it gets cold and as it gets hot, the soil is going to expand and contract, expand and contract, expand and contract, expand and contract. And so you see when it gets cold, it gets like this because of the water in there, and it contracts back down and it moves particle by 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 particle, and slowly you're going to get this creeping effect that's going to happen as you are moving along over time. And so eventually what will happen is the soil itself will creep its way down along the bedrock. Obviously the bedrock is the unweathered material that we are talking about in this case. Okay, and so what you're going to see now is a small little video where this actually happened in my backyard, over my old backyard, over a few years of just letting the soil expand and contract, and eventually worked its way down. So the next topic we're going to talk about is glacial erosion. We're going to talk about exactly what a glacier is and how it eats away at the surface, and then how it drops off that material that it picks up as it's eating away at the surface and what comes of it. This is by no means an exhaustive explanation, but it should give you guys a pretty good idea. Those of us in the United States that are watching this video, particularly in the northeastern United States, glaciers have shaped a lot of our landscapes, and even on the west coast of the United States, you'll see it as well. We'll see several examples of that, so that we can understand what is going on in our country of the United States. Those of you that are watching from outside the United States, you can understand what happened here in the United States to form it. I'm sure you've had geologic features in your environment that have been shaped by glacial erosion and deposition. Feel free to comment about that down below. So first thing we have to do is we have to talk about exactly what a glacier actually is. So what is a glacier? So the first thing we have to know is that a glacier is always going to form on land. It is a body of ice that physically moves, and it forms originally on land. So this is different from sea ice. This is different from the ice that forms on top of a lake in the winter. Okay, those are not glaciers. We're talking about a large body of ice that originally is going to form on land. Okay, it's going to form through this process called of accumulation. Basically, it piles up. Compaction, basically, it smushes itself, and recrystallization of the snow. Okay, now this all has to happen at a particular spot that's above what we call the snow line. The snow line being that point where snow exists year-round. Now, if you're at high latitudes in North Pole, South Pole, the snow line could be right at sea level. But the snow line, the closer you get to the equator, typically rises and rises and rises and rises. Okay, but there are snow lines even at the equator. You can have famous places, for example, like the snows of Mount Kilimanjaro, which are areas of Mount Kilimanjaro, which is very close to the equator in Africa, where you historically had large amounts of snow and even some valley glaciers and ice caps forming at those high altitudes at those relatively low latitudes. But if you're not at the equator, obviously it's going to be a little bit lower, and obviously most of our glaciers and things like that typically today either form at very, very high altitudes or at very, very high latitudes. Now, when we look at this, what we have to understand is that the process by which a glacier forms is going to be basically linked to what we see in this image here. So you start off with snow right here, and snow consists of about 90% air. You have a ton of air between these very, very pretty snowflakes, which is why when you're playing in the snow and you fall, it's like landing on a pillow. Okay, it's very soft. This is why when you go snowboarding or skiing or tubing and you fly off and land in a big pile of snow, you can laugh, and it's soft. There's lots of air there to kind of cushion. Now, as that snow accumulates, remember accumulate just means piles up, what starts to happen is the layer on top starts to push on the layer on the bottom. You add another layer on top, it starts to push on the bottom. Think of kind of like being underneath a blanket. You start off with snow, okay, you're laying underneath the blanket, it's nice and it's warm. Now imagine you fall asleep, people don't realize you're there at the party, and they start throwing coats on top of you. Well, what happens? You're accumulating coats. As you accumulate coats, the weight of those coats gets heavier and heavier, and there tends to be less and less space between you and the blanket. Okay, so there's less air. Eventually you get what we call granular ice, and if you look in granular ice, you see we're down to 50% air. Okay, and you can see that the shape of the snowflake is dramatically different. Okay, as that starts to pile up, you start to lose more and more of the air between the crystals, and you eventually end up with firn. Obviously a word that is not typical American English. Okay, many of the terms that we have for the studies of glaciers came from studies throughout Europe, particularly in France and other areas of Western Europe. But when you get to firn, what you basically have, firn is a word that means last year's snows, if I remember correctly, and you have 20 to 30% air. Remember, that's down from this original 90 that we had up here. And you can see that the shape of the ice crystals is dramatically different. You've lost a lot of the points between them, and you're going towards more of a rounded shape. Eventually you get to glacial ice, and glacial ice is some of the prettiest ice you'll ever see. A lot of times it has this brilliant bluish hue to it. It's some of the prettiest, cleanest, clearest stuff you'll ever see, and it consists of only a little bit of air, but that little bit of air can be really, really important. If you've ever heard of something called an ice core, it's something that a lot of climate scientists and other scientists will use. They'll drill into ice and they'll pull up these cores of ice, some of which could be thousands, if not tens of thousands of years. And although there's not a lot of air, those air bubbles that are in there are little samples of the air that was there when that original snow fell. So that can give us an indication of what the climatic conditions were like, what was in the air, and what pollutants were in the air, and things like that. This could help us to understand things like, the effects of volcanic eruptions. And we have actually correlated the air we found in some ice cores with certain volcanic eruptions that have happened around the planet, and that gives us an indication of how they've affected things. So these are super, super important things that you wouldn't necessarily think, oh, I'm going to study a glacier so I could study an ancient atmosphere, but it actually works out really, really well to understand these sorts of things. And so in this image here, you see a glacier right here, and down here you can see that beautiful glacial ice that we were talking about. Obviously up here you have a lot of material that's been carried, which we'll talk about, and that's the erosion and eventually the deposition that we're going to talk about in a couple of minutes. But once again, I just want you to look just as it's meeting the sea here. You can see this very, very clear, beautiful bluish ice that we were talking about. Now, when we talk about glacial movement, we have to understand that obviously this is not a super fast thing. Okay, glaciers are primarily going to move downhill, and the force that drives them is once against gravity, or their own weight, which weight being obviously a concept that is created by the gravitational field on a particular planet, notably our planet. And so basically what happens is, as you get a glacier forming in a hillside, the weight of the ice at the front of the glacier is going to pull down the material at the back of the glacier. And slowly, the glacier is going to flow down the valley that it exists in. Now, normally this is a very slow process. It wasn't 100% understood until scientists actually, once again, did what we did, do certain experiments where they marked different positions in the snow, and then they checked them over a period of weeks and months and years, and what we found out is that those positions slowly moved. Okay? And so if you look at the GIF that you see in the image in front of you, this is obviously time lapse of a glacier, but you can clearly see how the glacial ice is flowing downhill. It's being pulled down through these valleys. Okay, now something that you wouldn't see if you stared at it for a long period of time. A lot of that motion does tend to happen underneath, and there's lots of reasons, okay, and different causes behind the glacial motion. We don't have the time to talk about it here, but it's something that if you're interested in, you can obviously study. It's discussed a lot if you are to take, for example, a geology class as your freshman year college level course, or if it's just something you're interested, feel free. It's a world of information out there. Feel free to look it up. Anybody has any interesting videos or links, feel free to drop them down in the comments so that people can follow them. Now, as glaciers travel over land, what are they going to do? They're going to chew away at the land underneath them. They're going to chip and pull and rip off chunks of rocks. They're going to scratch. They're going to erode the bedrock underneath them as they move along the land. Okay? And they're capable of doing amazing things. A glacier can carry sand and silt and little pebbles, but they can also carry boulders that are several tons. Why? Because the glacier itself is several tons. So it can carry all the different sizes of sediments, and it can carry them from great distances. Once again, like I said, I'm over here in New York, and we have found rocks that were taken out of hills in Vermont, in Maine, samples that don't exist, that shouldn't exist in Long Island or in Westchester County, and they're discovered there. And when we date them and when we study them and when we chemically analyze them, we discover that they're from mountains that are hundreds of miles away. How did those rocks get there? They were carried by the glacier as it moved downhill. They can carry everything and anything that we would consider to be a sediment. They might be slow, but they are methodical and they get there. And so if you look in this image, you can actually see you've got all sorts of material. This is a glacier, and it looks like just a bunch of dirt, but that's how much material it's carrying. You can visibly see that you've got larger rocks here, and then much more finely powdered rocks. There's going to be material underneath it. It's just going to slowly drag all this with it. As the glacier moves, it transports everything, as you can see in the little image there. Little rocks, big rocks, and everything in between. It's going to erode the surface as you get freezing and melting cycles that happen underneath. It's going to abrade it. It's going to do all the things that we had talked about in our earlier weathering section. So how does it do this? Well, one way that we get glacial erosion is through abrasion. Remember, when you get rocks and material like that rubbing up against things, they're going to abrade it. They're going to smooth out rough edges and things like that. And so what you're eventually going to get is you're going to get what we refer to as rock flour, that comes out of these glaciers. Finely powdered material that's going to be escaping from these glaciers as the glacier melts or produces meltwater. So for example, here we have a glacier, large glacier emptying into a valley, and if you looked in this little zoomed out box over here, what you'll see is that all this little material is coming out as the glacier is melting through the meltwater. And you can see all these little fine bits of sediment that are being carried here. Okay, so basically as the ice flows along, you see the rocks that are inside the glacial ice are going to bounce against the bedrock, and they're going to chip and they're going to lose some of their sharper edges. It's also going to chip off portions of the bedrock beneath it. Okay, other thing you can get is what we refer to as quarrying or plucking. Okay, and if you look at this image here, what do you have? As the ice is, covering the bedrock and things like that, some of the pressure is actually going to cause water to form at the bottom of the glacier from the heat and the friction and just the pressure that's going on there. And so what happens is this meltwater can enter the cracks that naturally occur in the bedrock, which are these little black lines that you see here. As that water goes into the cracks, you're going to get frost wedging. We all learned about frost wedging. What's going to happen? Okay, it's going to expand, it's going to contract, it's going to expand, it's going to contract, and you're going to get rock fragments that break off. As the glacier flows down this way, what you're going to do is you're going to pluck, you're going to pull out chunks of rock and carry them downhill. Okay, and so you're going to end up with surfaces that get rounded out and smooth and abraded, and you're going to end up with areas that have bedrock that's been removed. So there used to be rock here and it's no longer gone. That's going to create lots of different depositional features that we're going to talk about in a little while. Okay, and so basically this is the process. Here you can see you get that frost wedging and that plucking as the glacier moves downhill. It's just going to pull these rocks off. It's going to pull these rocks off. It's going to pull these rocks off. Now the glacier is going to modify the land that it goes over. So what does that mean? It's going to change the existing landscape of the rock and the mountains and the hills and the valleys and the plains that it goes across. Okay, if it goes into a river valley, it's going to change those. Typically, a lot of times, glaciers are going to form in what used to be river valleys, what we call pre-existing river valley, and it's going to change it into what we call a glacial trough. And not only is it going to do that, but it's going to create all sorts of unique features that we have learned about and studied and named throughout the years. Okay, so for example, here you have a typical V-shaped valley. You can see the river running down it. Okay, you have a couple of mountains there. This would be during a period of non-glaciation. Okay, and let's say you have an ice age that comes through, Milankovitch cycles, all sorts of things that could occur that would change the climate in this particular region. And so you get a glacier that comes down. That glacier is going to fill in the valley, but you see what it did is it widened the valley greatly. You see how we went from a little V-shaped valley that we originally had to this much wider U-shaped valley that you have in the image here. And so typically that's going to be an indicator of what you get. You're also going to get all sorts of smaller valleys that occur up here as you get what we call tributary glaciers, glaciers that basically flow into the main glacier here, and they're going to form all sorts of interesting little features in the mountain ranges up here. You can see some of their names: Arête, Horn, Cirques, okay, and you're going to get all these interesting things. Now, eventually, we get out of that ice age, and the ice goes away, and we're left with a valley that looks like this. This U-shaped valley here is what we call a glacial trough. Huge indicator if you ever happen to be out about and see a valley that's shaped like this instead of the typical V, you're probably talking that a glacier carved its way through there. Then you have all these different horns and cirques and these different types of lakes and things like that. And so what you'll get is a valley that looks like this. Absolutely beautiful U-shaped valley. Imagine this was full of ice all the way up to here, carving and pushing its way out. You know, kind of like a snow shovel, just shoveling its way through all the ground, except instead of shoveling the snow was shoveling the ground. It's a crazy, crazy thing that you have going on here, but it's an absolutely beautiful image. And if you ever see a U-shaped valley like this in your brain, now you should go, hey, used to be a glacier there. Kind of cool. Okay, so when we look at those landforms, a couple things, a couple cool little things we want to talk about. One of them is this thing that we call a hanging valley. Okay, if we look at a hanging valley, what we basically have is you have those little tributary glaciers that we were just talking about that are feeding into the main glacier. And as they're feeding in, they hit the glacier, and so their ice just joins with it. Their material that they're transporting just joins with it. But that glacier was at a higher level, that tributary glacier was at a higher level than the main glacier. And so it never cut all the way down to the floor of where the main glacial trough is. So what you'll get is a smaller U-shaped valley feeding into a bigger U-shaped valley. Okay, and so what you end up getting is this basic thing right here, where you get what we call a hanging valley. So here you have your big glacial U-shaped valley. Here you have a smaller one. Now, a lot of times with glaciers, what we end up finding is we get these small little rivers that flow and things like that. And when you have a hanging valley and a river and a glacial trough, you can get an absolutely wonderful, wonderful waterfall like you have here in Yosemite National Park in the United States. Here you have your little hanging valley, and there you have a waterfall. These create some beautiful images. If you look online, there's a particular time during the year where when the sun is setting and it hits this water, it makes it look almost like it's fire coming out. Okay, it's a beautiful image. I advise any of you to go and look for it. It makes for just a really striking visual that you can see. Yosemite National Park in the United States is chock full of glacial features. If you ever manage to get out there, take some cool pictures, put them on the gram, feel free. You get a couple other features. Now, I know some of these terms are going to sound kind of weird, but you get these things called paternoster lakes, which are depressions that are formed by quarrying and abrasion that get filled in by some of that glacial meltwater. Now, this term paternoster is kind of weird. Like I said, a lot of the terms and things like that do come from the French. They're the ones that pioneered glacial studies. And to them, here you have your little paternoster lakes. You see them in the visual here. It's this chain of little lakes that are linked together by these little tributary rivers. And the term paternoster comes from the Catholic faith, saying that these river chains kind of appeared very similar to what would be a rosary, a Catholic rosary. And if you're familiar, or if you're not familiar with it, there are beads on the rosary that are points where Catholics would typically say the Our Father, or in Latin, the Pater Noster. And so to the French that were naming this, these little lakes appeared to follow that pattern, and so they gave it that name. Not something that's hugely important, but hey, if you're ever on Jeopardy, maybe you'll get the points. Remember us here at this channel. Feel free to drop us, a little bit of that money. I'm kidding. No, I'm not. If you want to, feel free. But they're really interesting little features that you might see. Visually, you can see here's three little ones that you can see here, the Paternoster Lakes right there. And so it's an interesting little feature that you can see with some of these. You can also get what's called a cirque. Okay, I hope I'm pronouncing that correctly. French is not my main tongue. Cirques are basically, you had a little valley where you had the accumulation happening of the snow over the years, and as it accumulated and built up, it carves out kind of a bowl-shaped valley, with one side of that bowl being open where the glacier would exit and expand and grow out of. Eventually, when the snow all melts, you can get a little lake that forms in the center of it that we call a tarn, which could be relatively deep and consist of some of this meltwater that was originally part of the glacier. And you can see it in the image up here. Okay, you have the tarn up here, and here you have a couple of the cirques that are forming right there and right there. Okay, over time, this image would be an image of an actual cirque that is currently still filled with some accumulating snow. You can see how it has the three sides here and kind of the bowl shape, and then the glacier's mouth is exiting out this way. This would be in an area where previously you would have had the glacier. Once again, you can see kind of the U-shaped valley. And there's your little tarn lake that you have right smack dab in the middle with your three sides there. Okay, one of the most famous forms that can form during periods of heavy glaciation and due to glaciers are what we call fjords, which is just a fun word to say. It's not fjords, it's fjords, obviously, not, once again, a typical American English kind of word, okay? And fjords are these long, narrow arms of the sea that extend really, really far inland, and they result from the flooding of a glacial valley. So what you basically have is, when we had our ice ages, the sea levels were much, much, much lower. The coastlines would have extended much, much further out to sea. And so as these glaciers were working down through these areas, they would have carved glacial valleys. Now, when the ice ages ended, the sea levels would have risen, and the ocean would have flooded back into those and flooded those valleys. And so what happens is you get these deep, deep, narrow valleys that extend really, really far inland. Okay? If that word sounds familiar, some of you may have heard it in the Frozen movies, some of you may have seen people talk about them. They make some absolutely stunning visuals. You can tour them, you can take riverboat trips. Obviously a dream of ours to go on one of these trips, and you can get some absolutely amazing pictures that you know, we all want to post it on social media and get absolutely awesome images. Here's one of them. That's a fjord that you could see here. That's an absolutely insane person sitting over a fjord, but it makes for a really, really cool picture. And once again, as the glaciers would have been moving through these mountains and carving these valleys, they would have been depositing material, and so you would get stuff like this. I don't recommend you do this. This is absolutely terrifying. I want to know where the heck the person was standing that took this picture, and I want to know who this guy is, because he's absolutely amazing at having taken that image. But it's just a really cool picture, and if you ever get a chance to do something like this, I would definitely recommend it. I'm going to link a video here of how you can tour some fjords and things like that, and what they actually would look like. That image will be showing up in a second. Another feature that we can get that forms because of glaciers are what we call horns and arêtes. I hope I said that right. I don't think I did. I'm sorry. And what we basically had happen with these is you get a cirque and it changes and it enlarges because of erosion. So one of the most famous examples of this would be this mountain in Europe known as the Matterhorn. Not the same ride as in Disney, but that's where it gets its name from. So the Matterhorn used to be a cirque, and what basically happened is the sides of it got eroded away, and so what you're left with is this very large, flat mountain, one of the most famous mountains in the world. Okay, and the arêtes would be these chains, which would basically, if you had two cirques next to each other, as time goes on, they're slowly going to get eroded away, eroded away, eroded away, and you're going to get this long, thin line of sharp, pointed rock that are forming between these two particular areas. The next glacial landform is just something that's just always fun to say. It's what we call a roche montagnée, I think. Again, French, not my language. These are primarily formed when you have continental ice sheets that are covering large chunks of the continents during like the ice ages and things like that. And basically what happens is these little hills are going to actually allow you to understand which way the ice sheet moved that actually formed these things. So what you basically get is you get a little hill of bedrock like this that's slightly resistant to weather and erosion. And as the ice flows along the top of it, what's going to happen is it's going to abrade one side and smooth one side out, and it's going to pluck this side. And when it plucks this side, it's basically going to pull out large chunks of the rock and then carry them down the ice flow. So what basically, when you look at these things, you can say, okay, so the gentle slope is going to tell you where the glacier was coming from, and the more inclined area of the hill, the steeper side of the hill, I couldn't think of the word for a second, is where you have the plucking, and therefore it tells you that's the direction in which it was going. And so if you look here, this is a roche montagnée, and you can see that here you have the gentle slope that was abraded, and then over here would be the side that you had the plucking. So the ice sheet that formed came from this direction and flowed in this direction, over this land mass that you're looking at in this particular image. Now, you get the erosion, you get the glacier, okay, cool. Well, all that stuff that the glacier picks up, it has to deposit. Remember, we talked about deposition earlier. Deposition is where you drop off all that sediment that you have now carried. So remember, it's a three-part: weathering to produce the sediment, erosion to move the sediment, deposition to drop off the sediment. So if we're talking about a glacier and the deposits that it lays, what are we talking about? Well, the material that a glacier is going to drop is what we call glacial drift. It's basically the sediments that a glacier drops off. Now, you have two main types. Okay, the first type is what we call till, and till is material that's deposited directly by a glacier. Now, a couple things that you have to know about till. Till is not going to be organized in any way, shape, or form. Okay, it is not differentiated. You're going to have pebbles and rocks and sand and boulders all mixed together. It is what we call unsorted deposits. Okay, and it's deposited directly by a glacier. Easiest way I could explain till is, imagine you had a snow shovel and you were pushing snow down your driveway or a sidewalk or something like that. As you push it along, you can get all that material that collects in front of the snow shovel. When you drop it off, when you stop pushing the shovel, you get that big pile of material at the front. That's all going to be till. You're going to have some big chunks of ice, some big chunks of snow, little powdery snow, little rocks, dirt, whatever happened to be along the way, all piled up in a big pile at the end. It was directly deposited by the shovel. Now, the other type of material that you can have is what we call stratified drift. Stratified drift is material that's deposited as the glacier melts. It produced by what's called melt water. So imagine you left that big pile of snow and it started to melt and water ran down into the street. Well, little bits of dust and dirt and sand and soil are going to get carried by that water and deposited maybe down at the end of the driveway or right by where it goes into the sewer. You see that pile of little material. That would be stratified drift. This is going to be sorted by size. As the water is moving faster, it can carry bigger stuff. As the water is moving slower, it can carry lighter and lighter and lighter stuff. So what you end up getting is this gradual progression from much larger, heavier material to much, much, much smaller material. So for example, if you look in the image here, you have a pile of till. You can see it's basically rocks and sand and silt and little bits of dirt and all mixed up, cobbles and all sorts of stuff. And then in the next image, you'll see what we would typically refer to as stratified drift, where you can see that it's much more organized and put together in a much better way. Okay. The last thing you can have is what we call a glacial erratic. A glacial erratic are these large boulders that can get carried by a glacier and get transported huge distances. Okay, we can see these glacial erratics all over the place. Once again, if you're in New York like I am, there are some incredibly famous ones in various parks. Central Park has a bunch of them. Parks throughout Queens and Brooklyn have tons and tons of them. Okay, and they're all over the place. Okay, in fact, when a lot of the settlers came down here and they found these, some of the big ones, they just had to leave where they are, so they made them like markstones or flagstones or things like that. Some of the boulders and stuff like that would have been used to create like rock walls and things like that. And so these glacial erratics are weird because they do not come from the native rock in the area. They've been transported huge distances. Like I was saying before, you get these rocks that come from Vermont and Maine and are deposited in Long Island or parts of New Jersey. So it's very interesting that they can be transported these huge distances by just these slow, progressive masses of ice. So when we talk about glacial deposits, your main glacial deposits that we're going to talk about, the first ones are what we call moraines. Moraines are these ridges of till. There's four basic types. You've got lateral moraines, medial moraines, end moraines, and ground moraines. Okay, so you get this big pile of unsorted material that's just kind of sitting there and all piled up. Okay, now when we look at them, it's kind of easy to see. So here you have a glacier. Okay, the lateral moraines are going to be the moraines that are out here on the outskirts of the glaciers. Okay, they're on the outer parts. So think lateral like in a football, you're pitching the ball to the side. Okay, the medial moraines are going to be right here along the center. So think about the medial line, right? If you're talking right smack dab in the middle of the glacier. Okay, and sometimes these medial moraines could actually be because you had two glaciers that came, two tributary glaciers that combined to form a larger glacier, which is probably what you have here, which is why you have multiple lines right smack dab in the middle. So once again, laterals are out here, medials are over here. Okay, this would be a ground moraine. So what is this? This is basically you had a glacier back here. As it melted, it deposited all this till here, unsorted rocks and pebbles and things like that. And finally, you tend to get these large end moraines right where the glaciers would have stopped. So if you look at the United States, you find these huge moraines all over the place. For example, in the Midwest, okay, you have these areas here in red and purple, which would be different end moraines for different glaciations that happened in particular periods in the United States. Okay, on the east coast of the United States, you see these quite often, particularly where I am, once again, over here in the Northeast in New York, along, for example, Long Island. Most of Long Island, which is this long island that you see here, a lot of it was formed either by till or by the deposits formed by glacier meltwater. So if you look along these red lines, these are these huge lines of terminal moraines that happened during different periods of glaciation. If you look in on these islands, and I'll show you some pictures, anything north of the island of this line is mostly till. It's hilly, it's bumpy. Anything south of it tends to be very, very flat because it's that stratified drift that we were talking about. And so you see these marked differences. So, for example, if you were to look at the hills, at the beaches and stuff like that on the southern part of Long Island, where my wife is from, you would find lots of these just piles of very organized, very sorted piles of glacial drift. So you get all this material that you can see. It's very uniform, it's very organized. Whereas opposed, if you went north of these lines, you get these big piles of boulders. An interesting little fact is if you ever come to New York, and you particularly come to the county called Queens, there's a line of demarcation where you can see this quite clearly. It's actually a road called Hillside Avenue. Everything north of Hillside Avenue is these piles of till. It's very bumpy, it's very steep. Okay, there's hills, there's all these things going on. Everything south of Hillside Avenue is incredibly flat. Okay, so areas like South Jamaica and things like that. On Long Island, in Nassau County and Suffolk County, you'll notice this as well. The northern shore of the island tends to be bumpy and hilly, and the southern shore tends to be much, much, much flatter. So it's something that you can actually see in the topography and in the land around you. So what about the stuff that isn't directly deposited by the glacier? What about the chunks of stratified drift that get pushed out? We call that outwash. So outwash is all the material that gets deposited by the melting ice after it flows over that end moraine. Remember, the end moraine is the moraine right at the front of the glacier that gets all the stuff as the glacier has pushed its way through. It's just laying right there. Okay? And so what you get is you get what's called an outwash plain or a valley train. So an outwash plain or a valley train is basically a really, really flat area just past the glacier that is really, really smooth and is basically consists of layers of sand and silt and clay that's been washed out. So if you look in the image here, you have the glacier back here. Right here is your terminal moraine, your end moraine right here. And then you have a little pocket of meltwater coming out here, and you can see how it's draining and creating this incredibly flat delta-like shape right here of sand and silt. So this would be here. Like I said before, if you look at a place like Long Island in New York State, the south shore of Long Island, south of like Hillside Avenue or that part of Nassau, Queens County, would be mostly this, and then the northern part would be all of this material that you see up here, all this landform that you see up here. Okay, and so here you have an image of a bunch of different moraines up here and an outwash plain. You can see the dramatic difference between the big hills of till and the big smooth flat plains of sand and silt that you have there as well. Now, when we have glaciers that occur, some of the things that can happen and some of the evidence that glaciers actually existed can be things like what we call glacial striations. So striations or cuff marks are basically lines that are made in the bedrock. As a glacier moves over bedrock, what it's basically going to do is it's going to grind that material that's underneath and against the bedrock and create these long parallel lines that we call striations that you can see. So for example, you see them right here, these lines that you see all along here. There would have been, imagine, a glacier sitting on top of this little chunks of rock, and as that glacier moved, it just cuts these lines. This is really cool. If you walk around New York City, Central Park, the Bronx, parts of Queens, you can actually see this in exposed bedrock all over the city. And that'll give you some indication as to the direction in which the glacier was moving, and just evidence that this major, huge metropolis 11,000 years ago was covered by these huge, massive continental ice sheets. And so this is basically what you would have. So you get these chatter marks that are created by these larger pieces of debris carried inside the glacier that are going to leave these marks like this that you see here. Okay, you get some polish caused by small particles, and then you get those striation marks like we see in the rocks, in the bedrock. So if you're ever out and about and you see things that look like this, that's an indication that the land that you're standing on had a glacier on top of it at some point. It's kind of cool. Okay. You also get the formation of lots of smaller little features that could be identifiers that a glacier once existed in the particular place that you were. For example, you get things like kettle lakes. Kettle lakes, basically, you get a chunk of ice that gets trapped in the outwash. So for example, there's the glacier, it stops, okay, and a chunk of ice breaks off of it and gets carried down by the meltwater and gets trapped. As that outwash washes out, it kind of covers up that ice. And obviously you cover ice with a bunch of dirt and dust, and the temperature goes up. That ice is going to melt. It's going to leave a big depression. That big depression is going to fill with water, and you get the formation of a kettle lake. For example, something like this. And this is Lake Ronkonkoma in Suffolk County in New York. It is a very, very deep lake, okay? And it is an example of a kettle lake that you see here in New York State. Hempstead Lake Park has a large lake called Hemp Lake. That would be another example of it as well. Okay, finger lakes are formed when a glacier deepened and dammed certain stream valleys. Okay, cut them in, kind of very similar to almost like the fjord thing, and it creates these long sinewy lakes. You find a lot of them in upper New York State. In fact, there's a region in New York State called the Finger Lakes region. If you look at it, you can see all these look like literally like big long fingers, fingers that have been dragged across the map. Okay, and they exist all over New York State, along with several other states as well, like Georgia and things like that. Okay, you can see it right here. This is the Finger Lakes region of New York State. It's literally called the Finger Lakes region. Okay. Another thing that you're going to get are these things called drumlins. Drumlins are these asymmetrical hills. They're about 15 to 16 meters high, so 45 to 180 feet high. They're not huge hills or things like that, and they tend to be shaped almost like teardrops. On one side of them, they tend to be steeper. On one side, they tend to be much more gentle, and they give you an indication as to the direction in which a particular glacier was moving. So if you see a bunch of these on a map, or you see a bunch of these in an area, that gives you an indicator of this. Okay, and so here you have a couple of them, and you can see the steeper sides here, and the more gentle sides going that way. And so that gives you an indicator of exactly which way the glacier was moving in these particular images. Here you have one by itself, where you can see it as well. Okay, you also get these things called eskers and kames. Eskers are just basically long ridges of stratified till that were deposited by rivers that were flowing through the glacier. So as the glacier was melting, the water coursing through that particular glacier would have deposited till inside of it, and so you get these long ridges of stratified till that were deposited. And then kames would just be large chunks of sediment that are deposited because you get a hole or a depression in the glacier, and that melts away and it leaves just a large amount of material there. So here you have an esker. You can see it's kind of snaking its way down through this image here. So this would all be a pile of till. Where you have a much flatter region here, that would have been what the glacier was sitting on top of. And then over here you have a kame, which is just this kind of hill. It doesn't have the characteristic, one side is steeper or smaller like a roche montagny or a drumlin. Now, glaciers can have effects on the ground that they lay on. Glaciers are big, heavy masses of ice. As they do this, they tend to make the crust underneath them deform and bend downwards underneath the weight. Think of it like a wooden floorboard with a bunch of weight on it. It's going to slowly deform over time. It's going to bend downwards. When that glacier melts, it's going to kind of slowly snap back into place. And so here you have a big amount of glacial ice, and that's going to push the ground down here. When you remove the ice, the mantle is going to rebound, and eventually, given enough time, it will return to its original place. Now, this video is getting a little longer than I had planned, so I'm going to cut it off here. And we'll do wind erosion and streams and all that other stuff in part 2 of this video. So I hope you enjoyed this one part, and feel free to jump on and watch the next one. I hope this was enjoyable, and like I said at the beginning, like, subscribe, and I'll see you guys later. All right, peace out. Bye.